Well, I'm either going to be brave or foolish in this podcast. I'm going to attempt another experiment or two. I'm going to start off by suspending a rectangle from a point. Where would you expect the center of mass to be if it's hanging freely under gravity? Well, if you look carefully, you can see a black cross on the cardboard, and that black cross is exactly behind the string. The string has a heavy weight on the end of it, so the string is hanging vertically, and the center of mass is hanging directly below the point of suspension of the rectangle. Now we have a triangle. No cheating, I'm just holding it very steadily, and if I'm honest, I'm being very lucky. You can see the three medians, and we know that the center of mass of the triangle is where the three medians meet. We're suspending from one vertex, and the center of mass is directly below where we're hanging it, and of course, the median is hidden by the piece of string. So when we suspend an object from a point and let it hang freely under gravity, the one thing that we can be sure of is that the center of mass will be vertically below the point at which we have suspended the object. Okay, now let's have a look at something else happening. Hey, wasn't that fun? Let's do it again. We just increase the slope slowly, 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 and as long as the box doesn't slide, it will fall over, it'll topple. Well, now, how is that connected with the center of mass? As we turn it up, slowly, 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 it's about to topple. It's just toppling now. Where is the center of mass at the moment? Just on that moment of toppling, what can you say about the center of mass? Well, let's cheat. Now you can see the center of mass. I've drawn the two diagonals on the side of the box, and you can see a black dot in the middle where the center of mass is. What's going to happen now as we do the same thing? We move it, the center of mass goes up and up and up. The whole lot's rising up. Look at the diagonal. What happens to the diagonal? Just about, and it's gone. Just managed to stop it. At the point where it's just about to tip, you should be able to see, without my cheating too much, that that diagonal there, this one, is vertical. And so we are tilting or toppling about the point at the bottom. So it's toppling about that. And when it's about to go, the center of mass is vertically above that point. So at the moment of toppling, the center of mass will be vertically above that point at the bottom. So those two ideas, that if you suspend an object, the center of mass must be directly below the point of suspension. If you increase the angle of a slope, provided that the object doesn't slip, then at the moment of toppling, the center of mass will be directly above that point about which it topples. Now let's look at a uniform lamina in the shape of an isosceles triangle ABC, where AB equals AC equals 5 and BC is 8. If we now suspend this triangle from the point C so that it hangs freely under gravity, how can we find the angle between CB and the downward vertical? Well, from what you've just seen, the center of mass, when the thing is hanging freely, will be vertically below C. So the first thing that we need to do is to find out where is the center of mass. Well, we know that the center of mass lies on a median, and we know that it lies 1/3 of the way up from the base. If we look at this triangle here, we have a right-angled triangle because isosceles and a median. We've got 4, we've got 5. The length of AM, therefore, is 3. So we have AM is 3. And therefore, the distance from G to M will be 1/3 of 3, which is 1. So we know now that G, as we found it, lies on the line GC, which is vertical when the thing is suspended. Just changing the color, I hope. And now let's look at a line from G to C. Okay, we know that that line GC is vertical. Just want to group everything, I hope. Group, and now comes the clever bit. We want the line GC to be vertical. I think that's near enough vertical. Then we go back to the pen. And now we're looking for the angle between the vertical and the line CB. We're looking for the angle between the vertical and CB. Let's call it alpha. This is 1. The side MC, which is lying on its side there, is 4. Tan alpha, therefore, is 1/4. If we look that up in our tables, we get that alpha, or in our calculator, is 14.036 ... We didn't really want that red dot, equals 14.0 degrees. So there is the angle between BC and the downward vertical when we are hanging the thing freely from C. Now let's look at a case of toppling. We have a uniform lamina in the shape of a rectangle, 8 by 6, and a square of side 4 has been removed, as shown in the diagram. The edge AB of the lamina is placed on a slope with A lower than B. If the lamina is about to topple, find the angle between the slope and the horizontal. Well, when the shape is about to topple, it will be turning about A. So the center of mass must be vertically above A. The first thing, therefore, that we have to do is to think about where is the center of mass. We can divide our shape up. We will have the rectangle. We can think of subtracting the square to give us the shape. We need to think about where the centers of mass of these pieces are. The center of mass of the rectangle will be at G1, where the distance from G1 to AB is 4. The center of mass of the square will be 2 in from the edge, and we'll call it G2. The center of mass of the shape itself will be some distance x bar from AB. The center of mass must lie, of course, on the line of symmetry. So we're only interested in where is the x coordinate. That is, of course, 8 by 6. So let's take that down, and now we should be quite used to finding centers of mass. The first thing that we're looking for is the mass of each piece, and with the lamina we think of that as the area. The area is proportional to the mass, so it will work just as well. The area of the rectangle is 8 times 6, which is 48. The area of the square is 4 times 4, which is 16. And we are taking one from the other so that the area of the shape is 48 minus 16, which is 32. We're looking at the distance of the center of mass from, and I choose to go from AB. So from AB, for the rectangle, the center of mass is 4. For the square, remember, is taken out from the rectangle, so that the square would be here. The center of mass of the square is 2 in from the midway. It'll be 4 plus 2. It will be 6 from AB. You can think of it, if you like, as 2 from 8. 6 will be the distance of the center of mass for the square. And then we have x bar, which is what we're looking for. We do sigma, not E, sigma mixi is equal to 4 times 48, that's 192, minus, because we're taking away the square, 6 times 16 is 96, and that will be equal to 32x bar. 192 minus 96 is 96. Divide by 32, and we've got that x bar is 96 over 32 is 3. So we know that our center of mass of the shape is 3 in from AB. Sorry, didn't mean to move it. 3 in from AB. Now we need to place that shape onto a slope so that the line from A to G3, it's still playing silly, what's it? The line from A to G is of length 3. So here we have a diagram. This was the point A and B, and here is the center of mass of G. We knew that it was 3 in from AB. The length of AB is 6. Half of AB is 3. And so the angle there, we've got a nice isosceles right-angled triangle. That angle must be 45. If that's 45, this angle is also 45, and so the angle made by the slope with the horizontal is going to be 45. You will find more in your textbook on pages 53 to 58.